Organic compounds that have same molecular formula but different arrangement of atoms are known as isomers. The existence of two or more organic compounds with the same molecular formula but different arrangement of atoms is called isomerism. There are two types of isomerism. The first one is the constitutional isomerism, or it can be referred as the structural isomerism, and the other one is the stereoisomerism. Molecules that have same molecular formula but different structural formula are called structural isomer. In the structural isomer, it can be divided into three different categories which describe more precisely how the isomers differ from one another. The first one is the chain isomerism. Chain isomerism are those which differ in the structure of their carbon chains, that is, they differ in the length of the straight chain or branches. While positional isomerism have the same carbon skeleton and belong to the same homologous series but differ in the position of the functional group. In general, the positional isomers have similar chemical properties because they have the same functional group. However, they have different physical properties. Functional group isomerism is shown by isomer which have the same molecular formula but contain different class of compound. In other words, these isomers have the same molecular formula but belong to different homologous series. To identify the chain isomerism from a given molecular formula, first you have to take out the general formula to identify the class of compound. Okay, so for example, here we have C5H12. So the general formula is CnH2n plus 2. So this general formula indicates that these compounds are an alkanes. So to find all the chain isomerism in C5H12, first we are going to draw the longest carbon skeleton, in this case 5 carbon. Alright, so I'm going to use the condensed structure. It's up to you if you want to use the expanded or skeleton. Okay, it's up to you as long as your structure is correct. Okay, so the longest carbon chain is 5. So I'm going to draw 5 carbon in a straight chain. 1, 2, 3, 4, 5. Okay, so this is my longest carbon chain, which is 5 carbon. Alright, so the first carbon got only one bonding here, so I'm going to put another 3 bonding, which is my hydrogen, okay, CH3, and then this carbon already got 2 bonding, so it's gonna need 2 more hydrogen. This carbon also got 2 bonding, so it's gonna need 2 more hydrogen. Right, 2 hydrogen, and the last carbon here got only 1 bonding, so it's gonna need 3 hydrogens. Okay, so let's count our carbon. 1, 2, 3, 4, 5. Our hydrogen, 3 plus 2 plus 2 plus 2 plus 3, it is 12. Right, so this is our first structure for the C5H12. Right, so the second step is from our longest carbon chain. Now we are going to reduce 1 carbon from this carbon chain. Okay, so originally it have 5 carbon. Okay, so now we are going to make it 4 carbon. Right, 1, 2, 3, 4. Another 1 carbon, we can put it here or here. We cannot put it here or here because these two is the terminal carbon. If you put another carbon here, okay, let's say you put it here, it's still gonna be 5 carbon longest chain. Same goes to here. So you cannot put it on the terminal, right? So we are going to put our another carbon here or here, but these two are from the same distance. If you put it here, it's still gonna be on carbon number 2. If you put it here, it's also gonna be carbon number 2. Alright, so it is symmetrical. Okay, these two carbon are symmetrical. So if you put it here or here, it's gonna be the same structure. So now let's put our hydrogen. So this carbon got 1 bonding, so it needs 3 hydrogen. This carbon also got 1 bonding, so it needs 3 hydrogen. This carbon got 3 bonding, it needs 1 hydrogen. 2 hydrogen, and 3 hydrogen. So now we have our second structure. Okay, if you learn the naming of the alkane, okay, in chapter 5, okay, you are going to know, you will know that the first structure name is the pentane. Okay, so we have pentane here, and the second structure here, actually it is 1, 2, 3, 4. Okay, so here we have 2-methyl butane. Okay, so from the nomenclature of these two structures, we can see that these two structure is not the same structure. Okay, so that's why it is an isomer to each other, right? It is a chain isomer because we are changing the longest carbon chain. Okay, we are changing the chain position. Next step, let's try to reduce another 1 carbon and make it 3 carbon longest chain. Right, so 1, 2, 3. So another 2 carbon, we are going to put both on the second carbon. Right, so here we have CH3, 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 and CH3. So still C5H12. Right, so can we make it shorter? Okay, can we make the longest carbon chain into 2? No, we cannot do that, because if we do that, okay, it's still gonna be 4 longest carbon chain. Let's try. Okay, so 1, 2. Okay, so if you put another 2 here, okay, and another one here, so it's gonna be longest carbon chain 1, 2, 3, 4. So no, we cannot make it shorter. So the nomenclature of this structure is going to be 1, 2, 3. So since 3 carbon longest chain, okay, so we have 2 methyls on the second carbon. So 2, 2 dimethyl propane. Okay, so there are 3 isomers in the C5H12 molecular formula. In positional isomerism, since we are going to change the position of the functional group, okay, it will need a functional group. Okay, for example, here I have C3H7Cl. So as usual, take out the general formula. From the general formula, we know that the functional group is halogen. It is from a class of compound haloalkane. Right, so first let's draw the longest carbon chain. Okay, so since we have 3 carbon here, right, so since we have 3 carbon here, right, so the longest carbon chain, 1, 2, 3, right, and then we are going to put our halogen, our functional group here on the first carbon. So the first carbon, it can be this carbon or this carbon. So let's say I'll put it here. Okay, so Cl, and then complete our structure with the hydrogen. Okay, so 1 bonding, so 3 hydrogen, 2 hydrogen, and 2 hydrogen. So now we have 3 carbon, 7 hydrogen, and 1 chlorine. Okay, so let's label our carbon. Okay, so since here is our first carbon, second carbon, or third carbon. Okay, so remember, if you put the Cl on the third carbon, it's still gonna be first carbon. Okay, and then we are going to change the position of our Cl. Okay, so now it is on the first carbon. Now we are going to make it we are going to put it at second carbon. Okay, so this is our carbon chain. Okay, so the carbon chain must be the same for the positional isomerism. Okay, we cannot change the carbon chain. Okay, it must have this, it must come from the same chain. Okay, the same carbon chain. All right, so now we are going to put our chlorine on the second carbon. Okay, and then put our hydrogen. Right, so the C3H7Cl only got 2 positional isomers. The functional group isomerism only involves these 4 general formula. From the first general formula, alright, CnH2n plus 2O, it can be either alcohol or ether. So the alcohol is the OH group, while the ether is the COC group. Okay, the oxygen in ether is going to be between two carbon. The oxygen in alcohol is on one carbon only. Another one bonding is with hydrogen, right? And then the second general formula is CnH2nO. It can be an aldehyde, which is the C double bond O with one hydrogen beside the C double bond O group, our carbonyl group. And for ketone, all right, so we have C double bond O C. So at both sides of the carbonyl compounds, it must have a carbon atom for ketone. Okay, another one is CnH2n. For the CnH2n, it can be an alkene, which is the C double bond C, and also a cycloalkane, C single bond C, which is it must consist of a ring. Okay, and then last but not least, we have CnH2nO2. Okay, so in CnH2nO2, it can be a carboxylic acid, which is C double bond OH, and ester, right? C double bond OOC. That's the difference. Okay, the oxygen in carboxylic acid must bonded with hydrogen. Okay, one hydrogen, while in ester, the hydrogen is changed into the carbon. Let's have a look at this example. The first one is we have C2H6O. So from the general formula, CnH2n plus 2O, we know that it can be an alcohol or ether. So let's draw our alcohol first. So the alcohol must contain the OH group. So we have the OH group, the hydroxyl group. Okay, so let's take out the longest carbon chain since we have two carbon here, right? So the longest carbon chain, of course, it cannot be one. Okay, it will be two carbon. All right, and then let's complete it with our hydrogen. So we have CH3, CH2OH. So this one is our alcohol. And then to change it into ether, the alkoxy functional group, which is CO C. Okay, the oxygen is between two carbon. All right, so this carbon is gonna need three hydrogen to complete the bonding. Okay, so CH3O, CH3. So we have two carbon, six hydrogen, and one oxygen. Right, and another example, C3H6O. From the general formula, we know that it can form aldehyde and ketone. So for aldehyde, right, the functional group is C double bond O, and it must have at least one hydrogen beside the C double bond O group, the carbonyl group. Right, so to complete our structure, so since it has three carbon, okay, so 1, 2, 3, and then let's put our hydrogen, so CH3, CH2, C double bond OH. So yes, we have 3 carbon, 6 hydrogen, and 1 oxygen. And to make it a ketone, okay, so the C double bond O must have carbon on both sides. Okay, so here we got 3 carbon. Okay, we already got 3 carbon, and then put the hydrogen. All right, put the hydrogen. So we have 3 carbon, 6 hydrogen, and 1 oxygen. So this is an aldehyde. This is a ketone.